Okay, welcome everybody to the I4 seminar on October 16th. And we're here with Professor Hovakimyan, who is a W. Grafton and Lillian B. Wilkins Professor of Mechanical Science and Engineering at the University of Illinois at Urbana-Champaign. She's a fellow and life member of AIAA, IEEE, a fellow of IEEE, member of SIAM, AMS, Society of Women Engineers, ASME, and ISDG. She's also the co-founder and chief scientist at Intelinair, which has been recognized as one of the fastest growing companies in the US. Her research interests are in control and optimization, autonomous system, machine learning, game theory, and their applications to aerospace, robotics, mechanical engineering, and agriculture. So she's going to talk to us about data-driven approaches for agriculture, and really looking forward to listening, Naira. So please take it.
Thank you so much for the introduction and for this invitation and opportunity to talk here. Like Girish mentioned, so I'm a faculty member in mechanical science and engineering. And one of the reasons that I developed this interest in agriculture has to do with my prior background of working with robotic applications, in particular with drones and flight control technology. We have a proven track record in aerospace applications, which naturally led us into robotic applications, drones and UAVs. And as I co-founded a company to grow into the space of data collection platforms, being located in Midwest, our first investments came from agriculture, and I found the field being extremely fascinating, like a junior industry being able to have great impact. But I had to learn agriculture, I had to learn a lot about farming practices, and being in academia, it's always interesting to explore new collaborative opportunities, to train students to collaborate across disciplines. And we were fortunate to have good business opportunities, good partners, and good academic collaborators. I worked a lot with Nico Martin from Crop Sciences. And today, here we are. So our interest started from kind of drones being as data collection platforms, and our first customers, farmers, taught us about the importance of finding the issues in farm at scale. So as you see here, it's a large farm, and if the prior method of finding the issues, like for example, weeds, nutrient deficiencies, equipment errors, and others had to do with lots of scouting, manual scouting, we could automate it with data collection from aerial platforms. Later, I had an exceptionally talented PhD student from Brazil who expressed interest in doing PhD in this field. And with the data intensive farm management project of University of Illinois that we work with David Bullock, so he did a PhD on nutrient optimization using the data collected at University of Illinois data intensive farm management project. He now graduated and works for Amazon. So this presentation will summarize the results we obtained in two projects. So let me get started. So as I said, I will present this agricultural vision, which is a large data set for pattern analysis that we did with my company, and also using some of the students from Tom Huang group at University of Illinois. And I will talk about this yield prediction model that we did with my student, nutrient optimization, and risk averse optimization of manageable crop inputs. So let's get started. So food security is a major problem. And as it has been already established, 69% more food calories will be needed in 2050 because of the growing Earth population. And we need to improve crop management in a sustainable, automated, and intelligent way. So here you see a picture that we had nicely grabbed from one of the posters a few years ago in one of the cyber physical systems conferences. So it nicely projects how the world population growth implies that we need more calories, for example, coming from different grains that shows up here. So we live in a world where the data collection has become very easy, cheap. So we get data from different sources, starting from satellites that we can get on daily basis for free, and we get lots of data through different machineries, through combines that do the seeding in the fields, through this agricultural machinery. We get it through crop health evaluation and prediction models. So these models can facilitate automated and intelligent decision making for better crop management. So what we show here is how the data growth helps us to build these various, for example, deep learning models that a farmer can use for real-time data management in the field. So here is a nice animation that has been produced by my company, showing these different issues that the farmers deal in the field on daily basis. This has to do with weeds, nutrients, pest disease, equipment, irrigation management, drainage, scouting. There are about 40 decisions per season that a farmer has to take during the year, and if these decisions are not correctly taken, the farmers can have billions of losses per year from bad decisions. So how we could help the farmers to take correct decisions if we get correct data collected and timely decisions given to the farmers through, for example, a correctly designed app, right? So this process, as we say, is this closed loop system. So coming from control background, I like to see everything in a closed loop system where with feedback, we help to improve the process. There is sensing that has to do with real-time data collection through, for example, through drones, through equipment, through soil sensors, combines, tractors. Girish has these ground robots that go under the canopy and so on. So equipment, satellites, data collection on all the levels from satellites to ground. And since we have used aerial images, I just list this here as number one. Then we do modeling. And the modeling, for example, again, I use the example that I will show in this presentation. It's a data set like this agricultural vision. I will discuss the particularities of this data set that we presented this year in the CVPR conference. The data set gives an opportunity to do feature extraction and to discuss how the data set can be used for modeling, which can be useful, for example, for analysis and prediction that we use here for different farmland patterns. So we build a learning model that can be used, for example, yield prediction, to do crop experiments, and to have models that can be useful as we go from one season to another to help the farmer to improve their decision every year, every other year. And these decisions, as we make, they can help us with optimization policies. For example, to help the crop insurance policymakers that how to develop these crop insurance policies that can help in future data collection, how to manage farm in a more optimal way in the 21st century, where we have this level of data science available to us, right? And so this is the entire closed loop system. And I will talk here about some particular solutions developed by my group through collaboration with my company and the crop sciences professors, Nico Martin and David Bullock, as much as we had over the last few years. So agricultural vision data set that we presented in the CVPR 2020 has to do with this kind of philosophy, right? How is my crop doing? This is a big question in every grower's mind, and only two ways to measure, right? One is the manual scouting that was there basically until the last few years, when basically drones and UAVs became available as viable platforms for data collection at scale. Although in my company, we do this with the help of Cessna platforms, which are manned aircraft, not UAVs, because the corn and soybean fields in the Midwest are so big that, I mean, doing it with UAVs and drones, it's just not optimal. You run out of batteries and flight time is essential. It will become too expensive. So we have manned flights so far at this point, but down the road, as the batteries become more efficient, obviously UAVs will be viable technology for this. So can we automate this process season long with machine learning to get complete visibility and have massively scalable algorithms that can help us to optimize this process and help farmers very efficiently to manage their season optimally. So this is the challenge that we have been addressing, and this is that led us to creation of this data set, agriculture vision. So let's see what goes here. So this data set is the first large-scale aerial agricultural image data set. If you are familiar with ImageNet, that was created by Fei Fei Li, who was a computer science professor at University of Illinois that created this ImageNet back in 2008-9. It was also first presented in CVPR workshop that led to this fundamental revolution in computer vision, making deep learning such a famous, prominent method. So she was just using Amazon Turks to label and categorize cats, dogs, and all these various famous objects. But agricultural image data set is very hard to label, because if all cats, dogs, and cars and tables and chairs all have similarities, then agricultural anomalies don't appear with such regular similarities. Weeds and different patterns that we see, they do not have such common similarities like human faces or these other objects that I mentioned. So it's very hard to group them, to cluster them, to do segmentation here on them. So, but we are up this challenge, and we have come up with a few methods that work here well. So agricultural vision data set is used for semantic segmentation of farmland patterns. These agricultural patterns are difficult to collect, but affect crop yields directly. So we have to come up with ways of collecting them, annotating them, and if we do it right, it has tremendous economic value. We can have great impact and help the farmers, essentially. The challenge for aerial farmland images, so that the data set requires inference over extremely large size images with extreme annotation sparsity. So we have built already a team of extremely skilled annotators who are going through these images with the help of our agronomists in the company, who are our crop science graduates, and they help us with annotating these images. And we work with farmers, our customers, who have their agronomists and computer scientists on their farm, who help us understand also these images very well and annotate and relate it to the true anomalies in their farm. So why is agriculture vision unique? It has color, channel, and ground resolution. Each image consists of RGB and near-infrared channels with resolution as high as 10 centimeters per pixel. Number of images, it's total 94,986 high-quality aerial images, which are collected from 3,432 different farmlands across the US. And the annotation is a total of 9 types of field anomaly patterns, are annotated based on their importance to farmers as well as other agricultural studies. Compared with other agricultural data sets, agricultural vision has larger data size, higher resolution, more types of annotations. As you see here, we have listed it here in comparison to others. These are references from our papers, a CVPR paper that you can go ahead and compare. We have listed the number of images, classes, labels, tasks, and if I go now one by one, I won't finish it during this presentation during this hour. And this here I mentioned that there is deep width that has only width annotations at image level, but there are 8 subcategories of width. So this is just to put things into the perspective for you. So the acquisition method, all images are captured by specialized mounted cameras on aerial vehicles. The camera types and the ground resolution settings are given in this table. The primary crop types in these farmlands are corn and soybean. So the color calibration, so for all 4 channels in one field image, we compute the 5th and 95th percentile pixel values, then clip all pixel values within the range. And the pattern annotation, annotators draw polygons around anomaly pattern. These annotations are then reviewed and corrected by expert agronomists. So to facilitate the model training and inference, so subsampling, full-size images can be as large as the figure shows above. We thus crop images into 512 standard sub-sized subsamples according to the geolocation of the annotated patterns, like we show here. And the cropping preserves the image resolution, so all subsampling images keep the 10 centimeter pixel ground resolution. Annotation region larger than 512 will be cropped into multiple sub-images. So this took lots of detailed work to understand how to make sure that the algorithms work with the best accuracy and the best resolution to give us the best performance. Annotation area versus class. The area of annotated regions for each category, images versus annotation ratio, and annotation area versus annotation, so are given in these kind of diagrams that you see. So And what we show here, for example, the number of pixels for these different, like I said, we do 9 different patterns. And these patterns, for example, dry down, nutrient deficiency are the types of anomalies that matter to the farmers. And for different type of anomalies, we have different levels, we have different number of pictures and different types of annotations that we have been able to use to come up with conclusions. And here we show the labels and the type of training, validation, and test sets that we have been able to get and to put into these diagrams. So the challenges that still exist after all these experiments that we have done over the past 2-3 years, we have highly imbalanced annotations across all classes. The uneven distribution between annotations and backgrounds is always present, and the region of patterns has great variations in size. So we deal with anomalies, for example, like equipment errors, can have more similarities in between, like turn rows, right? So the equipment that combine goes and turns comes back and plants, right? Or double planting. When they have double planting, it has to be removed because they compete for water and nutrients in the soil. These type of anomalies may have more similarities than weeds, for example. Weeds have very little similarities the way they appear and spread at different places. So this is what we mean. We have highly imbalanced data and annotations across all different classes, and this requires lots of attention to detail. That was very challenging, but we learned as we went through this work over the years. So the proposed network, so the FPN-based model for agriculture vision. So it was ResNet 101 with dilations as the backbone, 4 lateral connections, and then convolution upsampling layers. It shows improvement over conventional segmentation models across several patterns and also in general. So here we show the general MIOUs and class IOUs of semantic segmentation models and our proposed model on agriculture vision test set. So some details of these, how we did the validation, for example, are given in the CVPR paper. And if you go through it and have still questions, just feel free to email me. I would be happy to go with you over these questions as you have. I mean, here we show just our numbers that we surpassed the other methods wherever we surpassed. For example, here we did not surpass on the dry down. We were a bit less, like you see, but wherever we surpass, we show it with the bolts. And wherever we did not surpass, the difference is just a little bit kind of less, like you see. So model of yield response to nutrient management. Now I go to the second part of this presentation that had to do with the DIFM data at University of Illinois and what we did with Nico Martin and my student. Let me go and present this part of the work. So nutrient management optimization is critical, and excessive fertilization of crops that generate a surplus nutrient flow typically is known to pollute the water system and often reduce the productivity. Here are some examples that again we have taken from papers, and we'll give them the references here where to get these things. Let me present what's the data-driven approach here. So the DIFM project gives us the opportunity for crop experiments with some data that we generate the yield models. Optimization algorithm depends on the model, and prescriptions to farmers are generated by the end in the result of it. So we improve the crop management with data by modeling yield response to nutrient management using a multi-stream CNN with uncertainty quantification, and we optimize fertilizer and seed rate map using the previous model and risk constraints. And so a multi-stream CNN architecture for yield prediction that we have built is built using the following optimization model. So given a set as containing matrices representing the maps of environmental and managing variables, we want to approximate the nonlinear map such that what we have written here, that maps S to Rn, Y is the nonlinear map, Y is the crop yield map. So basically we have management variables, environmental variables here that we specify, and we want to build the yield map. So the management variables are the nitrogen and seed. The environmental variables are elevation, soil in EC, and we want to get the yield map out of it, right, which is a nonlinear map. The data-intensive farm management project has a large-scale on-farm checkboard trials with randomized nitrogen and seed rates that helps to create enough variability. So variable rate application equipment allows participating farmer to implement the designed experiment, right? And the yield monitor generates the yield data. My student actually traveled to Montana with David Bullock, and he was able to observe how these things happen in real world. He was very impressed by what he saw on the real farm. The data set consists of the data from 9 fields that were given from this DIFM project. The attribute variables are as follows. So it's the elevation map, nitrogen seed rate, electroconductivity, satellite picture, and the yield. The data type are polygons, the points, RGB image, and the units so are just mentioned here, what units we use. The key idea is to use information not only from a single point, but from a large area around it in a way that the spatial relations are figured out, which we mentioned here. So to improve the fertilizer management, a model for yield response to nitrogen and seed rates is necessary. So here we use some references in terms of what methods and models they have used, what variables they have prioritized, and the types of kernels that they have used. And as compared to these authors, this is our literature review that we have done. We have proposed the multi-stream CNN with the objective of yield prediction, so and emphasizing the variable importance of the spatial structure, and it's a learning-based kernel that we use. Okay, if some of you are familiar with these methods, then you would be able to understand what we bring as an advantage here. If not, so again, some more details are analyzed in our papers. And Alex's dissertation should be downloadable already from UC Ideals. So the dissertation will provide more details. So typically CNNs are used in feature classification problems. Inputs are usually images with a high level of correlation between channels, and different architectures are needed when dealing with multivariate problems, multiple inputs. So if we look again through some literature, again, we have done here some literature review. Again, I discuss here the problems that you see here in the first column, and the number of inputs. Again, these problems have different types of inputs. For example, action recognition in videos, you get 2 inputs, spatial and the optical flow. The architecture is a 2-stream CNN, and the fusion method is average of classifications from independent streams. So in our work, we propose a multi-stream architecture where inputs are non-linearly combined to address the yield predictions particularities. And now I will go ahead and describe a little bit more details. So it's a late fusion. So you see here our architectures that we've played with, right? The early fusion. So from late fusion, we go to early fusion, the 3D stack that will look like this. And our eventual method just basically ended up having the following architecture that you see here. So the average cross-validation results that got us to this following point. So we have RMS in over-normalized test set, and with the yield results presented here. And so what do we do with risk-averse optimization of manageable crop inputs, right? So and risk-averse optimization has to do with the fact that sometimes this optimization may not give the type of results that you expect, and the farmer must be sure before taking the risk. So we need to be able to quantify the uncertainty, because there is always uncertainty involved in these problems, right? And in stochastic optimization, we need to be able to understand how reliable are the data and how can we quantify the uncertainty to quantize the risk of the decisions, right? What is the risk in my decision? Because the farmers always care to understand how much risk they take before they proceed with a particular decisions. Imagine, I mean, every industry has their conservatism. And as I said in the beginning, I have worked long years with aerospace industry, and I found that aerospace industry is extremely conservative. For them to agree to change one parameter in a flight control design, it's extremely hard. But it's clear also, flight control systems are safety critical systems, and you obviously do not want to crash. it's a safety critical system, so you have to be very careful. Every small change there has to be done very conservatively. But then you come and deal with farmers, for example, who have their well-known practice, and you come and tell them, okay, I have collected your data, I've run my machine learning, I have a new way of managing your farm, a prescription algorithm or something, and they want to understand how much risk they will take to give up their known golden recipe and to follow your AI solution, right? So it's, again, you have to be able to quantify the risk and to tell them this is the risk you take and this is how much you can gain. And if you take this risk for a few years, you will generate some useful data that my optimization can do better over the years, right? So this is technology adoption path, right? If we want the technologies to be adopted, if we want to generate commercial value, if we want to scale these technologies, if we want to generate wealth, if we want to have societal impact, it's very important for us as scholars to be able to quantify the risk and to be able to communicate with the customers also. So we've tried to introduce some level of rigor here, and this paper is also already accepted for journal publication. So I just tried to explain here why we formulated this problem and how we formulated it, right? Trying to bring some rigor here. Prediction for distribution instead of a single output, quantification of uncertainty from data. So we did this with the help of deep ensemble framework. So it's MSE loss. We quantify like kind of least square means type of thing. We use heterozygotic NLL loss now with the help of this L function. And the output of the ensemble is the mixture of all output distributions. And so we're focusing on the uncertainty of models, right? And experiments with different number of members from the ensemble using the same 9 fields. So if we look through the illustration of log likelihood and standard error on the right, so we'll see the distribution of prediction standardized errors over the test set after training, how it changes dependent upon our kind of error definition over the 9 fields. And again, more details will be found in the dissertation and the paper. And here are our fields, here are 4, 5, 7 fields, so given as an example, and true yield, predicted yield, and the predicted standard deviation. So what we got here. The new model, so not only provides uncertainty quantification, but also outperforms its former version. So why risk averse optimization? So as we said, it's management variables, environmental variables, optimal yield map. So we find the optimal yield map by managing nitrogen and seed rate. Knowing when the input is far from the training data domain is important. As the search space is big, CNN model may find input maps with good results, but unlikely to work in practice. Constraint is needed for value at risk. So this value at risk is a well-known parameter in stochastic optimization. We actually use it also in stochastic model predictive type control applications in self-driving cars. So it's a value at risk is a known parameter also in autonomy type of research. So the problem formulation here we put like this. So if N and SB matrices representing the applied nitrogen and seed rate maps respectively, let's C and SB sets of matrices cropped from matrices N and S. So we define the total crop yield is then given by this nonlinear map. Also, let's define the net revenue as the crop value discounting the cost of nitrogen and seed. In our formulation, the net revenue is also a distribution in which we kind of define these variables in the following way. So by introducing this formulation, our optimization problem is written like this. Of course, we solve it with some solvers, ready solvers. So it's the expected net revenue, weighted uncertainty, subject to the following constraints. So optimal value at risk constraint. So this is how much risk the farmer may be willing to take or not to take. Expected net revenue will not be lower than raw with a confidence of 97%, for example. Safe and tested rates, right? To maximize the expected net revenue with var constraint already, to account for our var constraint, we reformulate our problem like this and apply the gradient ascent with the optimization problem. So we get to this point. So with this, I mean, more details are given already in the dissertation. If you are interested in looking through, so I summarized here, so automated crop intelligence, the value of automated crop intelligence for its potential to alleviate the issue of global food crisis. So we have to automate with the era of so much data being available at our fingertips. We can automate and have automated crop intelligence available at our fingertips. For that, we have built the agriculture vision, which is a large-scale agricultural data set. It's available from that agriculture vision CVPR workshop data set, CVPR workshop web page. The data set is available. People can download, can play with it, can try to write more papers around it, find more anomalies. It's open data set. We have released even a version of it for Amazon, for AWS to be used. A second version of it will be going to CVPR 2021 workshop. We're preparing now the second version of this data set, which may have more different types of data now added to it. So multi-stream CNN architecture for crop yield prediction outperforming existing models. We have done this with already Nico Martin and David Bullock using DIFM data sets here, not necessarily related to computer vision tools, but more machine learning and CNN architectures. We have leveraged deep ensemble framework to quantify the uncertainty in the predictions, and using these uncertainty quantifications, we have come up with risk-averse crop yield optimization using the quantified uncertainty with the use of proposed modeling and optimization framework. Experiments show an expected increase of 3.2% in the net revenue while reducing the management rates. With that, I want just to acknowledge our papers. It's a CVPR paper, CVPR workshop paper, computers and electronics in agriculture, 2 journal papers we already have. And for the first paper that appeared in March, just in 3 months, we had more than 7,000 downloads. It was acknowledged like the most downloaded paper of the journal in 3 months. The second paper was just published. Most likely within the next 3 months, it will also be one of the most downloaded papers of the journal. And I would like to acknowledge our sponsors. Alex is already with Amazon. I mean, our collaborators. Hong Kui-shi was Tom Huang's former postdoctoral fellow, PhD student, later postdoctoral fellow. He worked for IBM. Now he's a professor at University of Oregon. He guided the 2 students in Tom Huang's group for the CVPR paper. Nico Martin was our co-author on these papers on DIFM data sets that we did. Intelinair sponsored the 2 students for the CVPR project and also sponsored the CVPR workshop. CDA seed funding from UIUC sponsored Alex Barbosa's last year of PhD. With that, I am done. I can stop the sharing and happily take your questions, if any.